Okay, introduction to logics, and as we saw before, logics is the art of correct reasoning, the ability for us to reason correctly, and not everyone is able to think correctly because we all can think. This does not mean that we can think correctly. So we need to learn logic in order to reason things and reason them out in such a manner that we'll be able to get our things done correctly. Now, statements. This is the basic component of logic, and the statements must have a clear meaning, and it can be either true or false. It cannot be both at the same time. Questions, commands, vague sentences are not statements in logic, and everybody knows why. They cannot be proven to be true or false at the same time, so therefore they are out of logic. Now these are some examples of some statements and the non-statements. Today is a holiday is a statement, and are we having fun yet? Which is a question, is a non-statement. The square of 7 is 49 statement. It smells like wachama, non-statement, because that's vague. You don't know whether that's true or false. You don't know what wachama is. I did my homework, statement. This statement is true, non-statement. We don't know what statement we are referring to. Types of statements, we have the premise and the conclusion. Now, a premise is any statement or groups of statements which are used together and are supposed to provide evidence for a conclusion. And the conclusion, which is the other type of statement, is what we are trying to prove to be true. All right? Now, negative statements or negation of statements. Now, this is the process of changing a statement from what it is saying to the opposite meaning. So this means if a statement is considered true or it has been proven to be true, then the negation of that statement will have to be proven to be false, and vice versa. If it is false, then this negative will be true. So if S represents a statement, then not S, which is the negation of the statement, will be the negative or the opposite of what we had said before. For example, the statement, a triangle has 3 sides. The negative statement will be a triangle does not have 3 sides. Therefore, if you notice that the symbol for negation is this here, I think it's called a tilde, not sure. And if you notice that when you're trying to get the negative of a statement, you either use the not or you take out the not out of the statement. So, in most statements, to form the negation, you add or take away the not from that particular statement. And here we have some statements and their negations. Kai is running. Kai is not running. The not is added. All men are mortal. Some men are not mortal. The not is added. He is not a guitar player. He is a guitar player. The not is taken away. No birds are fish. Some birds are fish. Some women can swim. No woman can swim. So here we have some statements and we manipulated them in order to get the negation for those statements. Alright? And this now is the truth table for negation. The opposite in meaning true or false. So if P, which is true, not P, must be false. P, which is false, vice versa, not P, which will end up to be true. So if it's true and you want the opposite, it must be false. And if it's false and you want the opposite, it must be true. Alright? Conditional statements. Now these are important in logic because we use some conditions to test to see if a certain conclusion is correct. Now, when we use conditional statements, we use the if-then clause, and the if section is called the hypothesis or the antecedent, and the conclusion, which is the then clause, is also known as a consequent. For example, if you are a student, hypothesis, then you should study. Conclusion. So you have an if clause, hypothesis, and the then clause, which is called the conclusion. Now, let's look at some ways that we will manipulate or change around the conditional statement. And there are some statements that can be derived from changing around the conditional statement. If A, then B, that's the one we looked at. If you are a student, then you should study. Hypothesis, if you are a student, then you should study. Now, A implies B means that we are going to be implying instead of using the if-then syntax. Being a student, that means that it has been proven that you're a student. Then it must imply that you should study. All right? A denotes B. Being a student, one should study. And if you should notice, there's very little difference between A implies B and A denotes B. It's just a symbol that is used in the A denotes B. Alright? All A are B. Now this one goes a little further, but it proves that once you are a student, you should study, right? Therefore, all students should study. Alright? Related to conditional statements, we can change them and we will end up with three other basic types of statements: the converse, the inverse, or the contrapositive. Now the converse, B implies A or B denotes A, is actually you moving from top down to bottom up. So I'm moving from the conclusion to the hypothesis. So basically I'm spinning it around. The inverse, however, is going to be still using A implies B. However, we change it to negation. So negative A will imply negative B. Because once something is true, A proves B, then not A must prove not B. Right? We agree? Let me see the hands. Yes, Jermaine and Ruth. And the contrapositive now, on the other hand, is going to be turning it around where we are moving from the conclusion to the hypothesis and incorporating the negation as well. So therefore, not B, which is the conclusion, denotes not A, which is the hypothesis. Now, these statements are very important because they are used in creating arguments. And that argument has to be valid in logic because remember, we are studying the art of reasoning correctly. If it can be shown that a conditional statement is true, then its contrapositive must be always true. And it's logical because if I say A denotes B, then negative B must also denote A. However, the inverse and the converse can be both true or false depending on how we turn it around. However, the statement and its contrapositive must always be the same thing, either true or false. Okay? Now this is the truth table for the conditional statement. And please notice, if it is true, if P is true, then Q. P is true here, therefore Q must be true. So if P then Q gives you true. Fine? If P is true, then Q. Q is false, therefore the result must be false. We agree? Okay. If P, then Q. Therefore, we end up with it being true. P is false, Q is true, therefore, if P, then Q would automatically be true. Fine? And finally, if P, then Q, P is false, Q is false, therefore it must turn out to be true. Yes, Ruth, you have a question? I think you'll have to be chatting. Let me bring up my chat window. Okay, so I'll go over the truth table. Remember, this is the if P, then Q, right? Therefore, hello, I heard somebody a while ago.
I think that. Are you hearing me now?
Yes, Romain?
Yes.
Yes, I'm hearing you loud and clearly now.
Good.
Don't know what you did, but I'm hearing you now.
That's good. Okay.
All right. Okay, now for the sake of Ruth who asked, let's go over the truth table for the conditional table. Now, these are the headings, P, Q, then if P, then Q, right? If P, then Q, right? Therefore, P is true, Q is true, then it will automatically take the Q, which is true, right? Right, Ruth? Good. Now, the second one, if P, then Q, then it will automatically take the Q again. Okay? Right. The third one, if P, then Q, it will take the Q again. Right. However, in the last one, both are false. You see that, Ruth? Hence, it will not take the Q because both are false and therefore will end up to be taken as the true. I was talking too fast. I can continue. Should I continue, Ruth? Okay. All right, so going back now to our logic. Now we'll be moving from statements. Now that we're clear about statements, statements are what are used to create arguments. Now we argue every day, but do we argue correctly? An argument must be valid in logic for us to consider it to be an argument. Now, in order to create an argument, it must be considered to consist of some sets of statements, one of which is going to be the conclusion. And that is what we are proving or trying to prove to be true. Now, this conclusion, because only one conclusion must be in any argument, it must be supported by some other statements which are called premises. Statements which are supposed to be supporting evidences for the conclusion. Now let's look at this. Is this an argument? Miss Malaprop left her house this morning. Whenever she does this, it rains. Therefore, the moon is made of blue cheese. What say you? Is this an argument? Or should I say, is this a valid argument?
It can be a valid argument up to point 2. Point 3 doesn't come in any at all, because if it is noted that whenever she left her house, it rains. We could put some argument to that, but the third point, therefore the moon is made of blue cheese, has nothing to do with her leaving the house, or because of her leaving the house it rains. It's like it's separate and apart. So I would not say that would be classified as an argument.
Okay, and good point. But however, it cannot logically be classified as an argument.
Right.
And the reason why that you gave is the reason why it cannot be logically defined as an argument. Remember, there must be a conclusion that ties into the premises. And this conclusion has nothing to do with Miss Malaprop leaving her house or it's raining. So therefore, it cannot be considered as a valid argument. Okay? But you are right on point, Romain. Any question, Ruth? Okay. Now let's look at what makes up a good argument. An argument is valid if and only if the conclusion must be true given the truth of the premises. And those are the ones that are going to be used to tie in with the conclusion. Now let's look at this other argument. Is it valid? If the moon is made of blue cheese, then pigs fly. The moon is made of blue cheese, therefore pigs fly.
Well, that one is a clear argument, because all the premises leads up to the conclusion.
Right, and everything ties in and is related. Yes,
Right.
Ruth, I'm seeing your signal that yes, you agree with us. Okay, and if you have anything to say that we cannot use it a yes or no, please feel free to write it in the chat corner, okay? Now, please remember that once you're making an argument or you have to prove that an argument is valid, it must tie into the conclusion. So the premises 1, 2, 3, or 4, depending on how many premises you use, must at the end of the day tie in with whatever you're trying to prove. So you can't be saying it is raining, however, you're at your computer. What does the rain have to do with you being at your computer? It must have a middle ground to tie into the conclusion. Alright? Alright, now an argument is sound if and only if the argument is valid, and in addition, all of its premises are true. So if we go back to the argument we looked at, is this argument true and not true, sorry, is it valid and sound at the same time? What say you? Romain, you're saying it's sound as well? Okay.
I
Ruth?
think it's valid and sound.
You think it's valid and sound?
Yes.
Ruth? Yes or no? Is it sound as well? Okay, well, I disagree with you both. Now, if we should go back, an argument is sound if and only if the argument is valid, and we proved it to be valid, and in addition, all of its premises are true. Now, let's look back at the arguments that were presented. If the moon is made of blue cheese, then pigs fly. Is that true in and of itself?
No, in the literal sense, it's not true.
Yes.
But then it is a statement. So you know, you're saying if the moon is made of blue cheese, then pigs will fly. Then we realize now that hey, the moon is made of blue cheese, so therefore the only logical conclusion is therefore pigs are going to fly. So even though it is not valid in the literal sense, it is still a statement, and the premise is linked, and then
so
the
therefore
conclusion
you're saying it is sound.
Yes.
Okay, I was just pulling your legs there a while ago because I wanted to get you thinking logically. So yes, it is indeed valid and sound at the same time. All right?
Okay.
All right. So after that bit of logical thinking, we'll now move on to reasoning processes used in creating arguments. And believe it or not, we use it every day. It's either we induce logic or we deduce logic. So therefore, the two reasoning processes that are used with logic are induction and deduction. What do these mean? Induction is a reasoning process in which conclusions are made after we observe results. And these results can be garnered from experiments or experiences that were analyzed, or some authorities that cited some things, or some statistics that were presented to us. Future experiences are now predicted by extending the patterns that were gathered from present experiences. All right, so we can predict future experiences by looking at present experiences and trying to extend the pattern to see what is going to be the result. And this is what I guess they use with weather patterns and stuff to tell you, okay, it's going to rain tomorrow or whatever not, be true or false sometimes, but this is a way of saying we are inducing some thinking process or reasoning process, all right? And if you look at this diagram here, we have to observe first, induce, which is us thinking inductively, and then coming to a set of conclusion based on what we have observed, all right, or gathered. Now, inductive reasoning is a process of determining a general conclusion after we have examined individual cases or some facts. And when we reason inductively, we have to ensure that there is sufficient facts, as your conclusion might seem true, but you'll not be able to be certain unless you have enough facts. For example, the first 10 people you meet at school are nice. So you might tend to generalize that, hi, CIT is so friendly. However, the 11th person you come across might be hostile. And this one person would falsify your conclusion that you had made before. All right? So once you're reasoning inductively, you must ensure that you have enough facts to support your conclusion. Scientists repeat experiments multiple times, and this is the main reason behind it. Before you arrive at a conclusion, that you have to test and get enough information. Please note, a good inductive argument only gives a high probability that a statement is true. So we therefore say if it's 99% true, then we say it is true, or that an action should be performed. But once you cannot say it's 100%, you're not using inductive. Inductive means that you are saying it's a high probability that it will happen this way, but I am not, or I cannot say that it is 100% accurate. All right? So please know that. Deduction, on the other hand, is a reasoning process in which conclusions are based on accepted premises, which are usually articles of faith, some rules, some laws, definitions, assumptions, or commonly accepted facts. The conclusions are reached explicitly or implicitly and based on premises that are contained in this argument. Now, you have to have a set of rules that were there before, or laws, or whatever you have. And then based on these laws, then you deduce your new conclusion, all right? The deductive argument consists of a series of statements, premises, and a conclusion, where the premises are usually written as conditional statements. That's what we looked at before. And these arguments may take different forms. Now, one of the common forms of deductive reasoning is syllogism. And syllogism consists of two statements, only two statements, and a logical conclusion being drawn from these two statements. All right? Now, hypothetical syllogism, affirming the antecedent and denying the consequence, are the three types of syllogism that we will look at. And please remember, a syllogism contains how many premises? How many premises does a syllogism have? I should repeat, Romain.
Yes, could you just go back a little bit to the previous slide? I didn't get that from it.
So I should start back at syllogism or go back to deductive reasoning?
No, I get the deductive and the inductive. The syllogism.
All right. Syllogism. A syllogism consists of two statements, which are called premises, right? And the third statement is called a conclusion, which we have drawn from the two premises that were stated before, similar to the arguments that we looked at before. However, a syllogism must have only two statements. All right? Now, the types of syllogism that we'll be looking at are hypothetical syllogism, affirming the antecedent, and denying the consequence. All right? And a syllogism, for emphasis, has two statements and a conclusion which follows. Two premise and a conclusion. So in all, three statements, two being the premise and one being the conclusion. So it's like two if-then clauses, then a conclusion. All right? Let's look at the hypothetical syllogism. If a triangle is isosceles, then it has two equal sides. Is this true or false, class?
That is true.
That is true. Now, second premise. If a triangle has two equal sides, then it has two equal angles. True or false?
That is true as well.
Therefore, an isosceles triangle has two equal angles. Is this true?
Yes.
Was it proven to be true?
Not 100. Not I just say 100% proven to be true, because for us to get that 100%, we would have to actually measure, and there was no measurement going. It's just a statement. Based on these statements, then we could say yes. Based on these two statements before, we could say yes, that's it's true, but not 100. We can't say yes, it's 100% true. But based on it, if
no, we're not looking.
then we could say yes, it's
If
true.
you are just following this?
The two statements before, then we could say it's true.
Right, and remember that syllogism, which is deductive reasoning, is based on some facts that were proven to be true before. And we know that an isosceles triangle has two equal sides, right? And if a triangle has two equal sides, then it goes to prove, which was proven before too, that it has two equal angles as well. So therefore, the isosceles triangle has two equal angles. Now, if we use the rules that were proven before we were born, along with these sets of arguments, we end up with a syllogism where the two premises come to a conclusion where an isosceles triangle has two equal angles. Because if a triangle is isosceles, then it has two equal sides. And if a triangle has two equal sides, then it has two equal angles. Alright? Any question on the hypothetical syllogism? Okay. Affirming the antecedent. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. What say you about this? Affirming the antecedent. Alright, so Ruth is saying that it is in fact true. We agree, Romain?
I'm not so sure. I'm not so sure.
You're not sure?
No.
Are all men mortal?
No.
No. Who is immortal?
Oh, sorry. Yes. All men are mortal. Sorry.
Alright. Is Socrates a man?
I don't know what is a Socrates.
Oh, I'm sorry. Socrates is a man, a Greek man, a philosopher who dated way back in the maybe 17th or 18th century. So yes, he is a man. He was maybe a mathematical philosopher. Right.
Okay,
right.
now I get it.
Sorry
I
about
get it.
that.
So yes, that is true.
Okay.
That is true because all men are mortal. That is correct. So
Uh-huh.
that's first statement.
So that first statement is correct. Right.
Right. Socrates is a man, so therefore he must be more. Yes. Yeah, I agree.
Right. Now, one thing I must point out is that the ending must be the starting in the second statement. The ending in the first statement must be the starting in the second statement. And as you will see in both the hypothetical and affirming the antecedent syllogism, you will see that we end with equal sides and we start out if a triangle has two equal sides. Here, the first statement, all men are mortal, then we start out that Socrates is a man. So therefore, the second must tie in with the first one in order for the third, which we are trying to prove to be true, to be true. All right? Now deny the consequence. If you pay the bill on time, you are not charged a penalty, right? You are charged a penalty. What does that imply? Therefore, you did not pay the bill on time. Do we agree? Right, and JPS comes to mind readily. If you do not pay the bill on time, then you will get charged. You'll even get cut off. So, once more for emphasis, the three types of syllogisms are hypothetical, affirming the antecedent, and denying the consequence. Alright? Now, these are some symbols that are used with logic. You know the first one already, you've been introduced to it. But the others, this is the therefore symbol. The conditional symbol is the arrow. And that is if-then, the if-then clause. Equivalent statements, that means that, for example, the statement where you say A implies B and the contrapositive, those were logically equivalent. So therefore, this is what you would use for the symbol to say that two sets of statements are logically equivalent. All right? The conjunction symbol is the arrow pointed up, and the OR symbol is the arrow pointing down. Okay? So please remember your symbols that are used in logic. And don't worry, your break is coming up. Just let me hurry and finish up. We would have finished if we were not going through some technical difficulty before. All right, I'm just checking to see if there are any questions from Ruth. If not, we'll continue with our truth tables. The first one we'll look at is the OR truth table, which is called disjunction. Marion Jones is worried that she's not going to win a medal in the 04 Olympic Games. Her husband assures her that she will surely place in one of the two events she has qualified for. It's okay, he says. Either you'll medal in the long jump or in the 400-meter relay. Fine? So let's look at the truth table for this, bearing in mind that she will either medal in one or the other. That means you must have two conditions, two things in which one of them can end up to be positive, right? Okay, so let's look here. These are the two conditions, P or Q. P is true, Q is true, so P or Q would end up to be true. The second one, P is true, Q is false, so P or Q would end up to still be true. So Ruth wants me to repeat the scenario. That's the example with Marion Jones, I'm assuming. If we go back to Marion Jones's example, she's worried that she's not going to win any medal at all in the 04 Olympic Games. However, her husband assures her, and this is what he says to her. It's okay. Either you'll medal in the long jump or in the 400-meter relay, right? So it's either she's going to get one medal in the long jump or in the 400-meter relay, but she will end up with a medal at least. All right? That's clear now, Ruth? Okay. Now let's go back to our table. P is true, Q is true. P or Q will end up to be true. Do we agree? Okay. Ruth, how about you? All right. Now let's look at the second one. P is true, Q is false. What's the result for P or Q given P is true and Q is false?
I agree that it will be true.
You agree that it would be true, given the fact that?
Given the fact that we have one, based on the statements that we would be gathering, one of it can be proven.
Okay. So therefore, once one of the statements is proven to be true, then the result will end up to be
true.
True. Right. So let's look at the remaining two. P is false, Q is true. So the result must be true. P is false, Q is false. So this time P or Q cannot be anything but false. All right. Are there any questions on the OR table or the disjunction truth table? Okay, since there are no more questions, let's move on to the meaning behind the OR truth table. A sentence in the form P or Q is true if and only if either P is true or Q is true, as Romain explained to us a while ago, or both P and Q are true, otherwise it is false. So, in the words of Romain, just as long as one condition is true, then the result will be true. The two sentences P and Q are known as disjuncts, and hence we get the word disjunction for the OR truth table. Are there any questions? All right, moving on to conjunction. Now, this is our truth table for the conjunction. Now, let's say Marion Jones was worried about getting a medal in both events, both the long jump and the 400 meter. This would be the scenario, right? P is true and Q is true. Therefore, P and Q would be true. Do we agree? All right. P is true and Q is false. Therefore, the result is going to be false. P is false and Q is true. Therefore, the result is going to be false. And the last one, which is self-explanatory, P is false and Q is false. Therefore, the result for P and Q is going to be false. All right, so do we agree with this truth table?
So basically, this one is the opposite of the first, the OR.
Not really opposite, because the two of them have the same result for true and true. But basically, it's the opposite logical thinking. Okay. Hello?
Because once there's some form of like doubt, because you have P is true, Q false. Therefore, in this scenario, you would not be the outcome cannot be 100% true. So you cannot be sure of the outcome. So there could be the result could either be true or false. So it would stick to the is it that they're saying that the more logical answer would be to say it would be false?
Yes, because we are not 100% sure that both conditions are true. So therefore, it has to be false. And Ruth, I'm seeing your question, but I'm just finishing up with Romain. Hello, you're hearing me?
Disconnected.
No, Romain, you're not disconnected. Hello, you're hearing me?
Yes,
okay, you're not disconnected. I'm not sure what happened a while ago. But Ruth, I'm seeing your question. I'll get to you in a bit. But as we were saying, Romain, both conditions have to be proven without a doubt to be true for the result for the AND to be true. Okay. All right?
Yes.
So Ruth, would you like me to go over the principles of the AND truth table? Okay. Therefore, let's go. These are the two conditions. Marion Jones wants to know if she's going to be winning a medal in both the 400 meter and the long jump event.
Brenda, hello?
Yes. Hello.
Okay. Yes. I guess for Ruth to better understand, she must look at the word and or. So if P is true and Q is true, it has to be true. And
Right.
if you put the order, right, so that's the principle right there. So you have to make sure you put those in. So if you say P is true and Q is right, let's say it's false. So P is true, but Q is false. Your answer cannot be true.
Because both are not true.
Exactly.
Right.
But if you look at the or no side of it, if you say P is true or so you see the and would make sure that both of them would have to go hand in hand. See, the one would depend on the other for us to get a conclusion. But with the or, once one is true, then we can always eliminate the other one because it's one or the other.
That so we could be true.
Right.
All right. So are we clear on our rules? Have to be proven to be true without a doubt for it to be true. Yes, that's correct rules. All right, so I'll be continuing now. So look at the reasoning behind the truth table, which I think we have pretty much covered. A sentence in the form of P and Q is true if and only if P is true and Q is true. Otherwise, it is false. So both statements must be true for it to be true. Now, these two sentences, P and Q, are known as the conjuncts. Therefore, we get the term conjunction for the and truth table. All right? And please remember, disjunction is or, conjunction is and. And I guess you will remember conjunction, but just try and remember the disjunction, all right? And here we are looking at the negative truth table again, just for a reminder. Anything that isn't true, if P is true, then not P would be false. And if P is false, then not P would end up to be true. So here we have the opposites coming out again for the negative truth table. A sentence in the form not P is true if and only if P is false. Otherwise, it is false. So, logically speaking, negation has the effect of switching the truth value of any sentence in which it occurs. So, we're looking at opposites here. If it's true, then not true is false, and if it is false, then not false is true. All right? Any questions so far? Okay. All right, let's look at the truth table for the conditional if-then. The material conditional is most naturally represented by the phrase, the English phrase if-then. For example, if you study hard in this class, you will do well. Do you agree? Right. And you had get some yeses from you for that one. Now let's look at the truth table for the conditional clause. If P is true, and this again is a refresher, if P is true, then Q, which is true. If P is true, then Q, which is false. If P is, then Q, which is true. And if, because both are false, then we end up with the true. All right? Now, a sentence of the form, if P then Q is true, if and only if either P is false or Q is true. Otherwise, it is false. So, if either P is false or Q is true, then Either P or Q is false, then it is true. Otherwise, if both are false, then it will be false. Alright? So that's the way for knowing the if then. Both of them have to be false for it to be false. Okay? So that's the end of our logical thinking. Are there any questions at this time?
Brenda?
Yes.
Could you, the last part, it kind of slipped me just a little bit. Could you go right?
The conditional if then?
Right.
All right, so let's start back here at the truth table. This is fine, Romain?
Yes, that's fine.
All right. Now remember, we are saying if P, then Q. Fine? Now, we automatically take the, sorry about that, we automatically take the value of Q because we are saying if P, then we want to take the value of Q. The only time we do not take the value of Q is when both P and the Q are false in essence. So let's look at the truth table again. P is true. So if P is true, then we say the value of Q, which is true. Fine? If P, the second one, P is true, we take the value of Q, which is false. If P, which is false, we take the value of Q, which is true, because Q is not false as well. So we come down to the last one, which says P is false and the Q is false. Therefore, the result cannot be what Q is, but true, the opposite of what Q is. So in other words, the conditional if-then truth table must take the value of the Q unless both conditions are false. Once both conditions are false, then we do not take the Q value, but the opposite, the Q value. Are we together? Right. Okay. So are there any other questions? No? Okay, well, it's my turn to ask the question. Right before you go on your lunch break, you'll just take lunch and break together, then you'll come back for your assignment. What is logics, Ruth? And please type it up for me so I'll be able to read it. Logic is the science of correct reasoning. That's correct. Romain, what's the other name for the OR truth table? Waiting on Romain. The other name for the OR truth table.
I'm trying to remember. It's the the and one is the conjunction.
Yeah, no, you would remember the and.
Yeah. I remember the and one. So would it be this? Is it a disjunction or?
Yes, it is in fact the disjunction. All right. So I'm glad to know you guys are paying attention, and you have actually finished the first topic in your program for the summer. Your exercise in the classroom, Romain, I'm not sure if you have access to it. So what I'll do is, wow, I'll have to email it to you guys because I'm not 100% sure that you have it. So what I'll do is